So irrespective of the numbers that they give you, the basic relationships are the same. We know the velocity, the orbital velocity or the orbital period. Which one do we know? The velocity of the inner one, right? All right, so this is V1. So planet or satellite R1 rotates with the speed of V1, and satellite 2 with the radius of R2 is going to have, first of all, tell me, is the speed, the orbital speed, going to be greater or less than that of the inner satellite? How do you guys vote for it's going to be faster? It's going to be going faster. The second one, the green one. The green one is going to have an orbital period that is greater because the speed is less. The speed, what we're solving for speed. So speed is greater. Yes, that is correct. Okay, speed is greater, orbital period will be less. Okay? All right, so let's take a look at what we know. And so we know we're dealing with centripetal force. And what flavor of that equation are we going to use? The easy one. mv squared over r is correct. Okay? So we're going to have two different mv squared over r's. Is the centripetal force, now look, is this true? Is this true? Why is this not true? Okay, what does this statement say? What does this statement say? All right, let's say, Mike, what does this statement say? Okay, are their centripetal forces equal? No, and how do we know that their centripetal forces aren't equal? Okay, because their radii are different, but that tells us that something else is different. What's different at different radii orbiting the same mass? The amount of what? The amount of gravitational force, okay? So if the gravitational force is not, gravitational forces are not equal at those two different distances, their centripetal forces can't be, because guess what? Their centripetal forces are equal to their gravitational forces, each one of them, right? At their individual places. So this is not true. This is a very easy mistake to make on this problem, but it is not true. All right? So how are we going to approach this? We know in general, when centripetal force is equal to gravitational force, write it like this: centripetal force is equal to gravitational force. What's our expression? We're using velocity. So what's our expression for centripetal force going to be? As we said already, mv squared over r. We'll use a capital R. I'll explain the difference between capital R and little r when we do astronomical things in a second. All right, that is equal to what? What's the gravitational force? How are we going to take care of that? Right, we're going to use universal gravitation. So big G times, what's big M in this case? That's the central gravitational mass, correct. What is this little m? That's the mass of the satellite, okay? But what are we going to see here in a second? That's right, snow day at the Vatican. Mass is canceled. So now we have v squared is equal to v squared over r is equal to gm over r squared. Now, is this true for satellite 1? Yes. Is this true for satellite 2? Yes, this is a generalized expression equating centripetal force and gravitational force, right? And because gravitation, this is what Christy was saying earlier, because gravitational forces is not the same, then the centripetal forces are not the same. But something's the same. In fact, a couple of things are the same. Well, G's a constant, so that's a giveaway. We know that's the same for each of them. What up? Yes, the mass that they're orbiting is the same for each one of them. Okay? You got that? So, in each case, v squared over r. Now look, how about if we do this? If we say, yep, that's exactly what we're going to do. We're going to cancel out one of the r's, and this goes away, this goes away. So we get v squared is equal to gm over r. Now this is another technique that we use in physics a lot. so that we can see the relationship of variables. If we've got some constants and some variables in the same equation, but we've got two different sets of things that this relationship is true for. Okay, this relationship is true for both satellite 1 and satellite 2. So if we put the constants on one side, watch what happens. Now we get planet, which one was blue? The inner planet was blue. So let's say, we're going to say v squared r. This is another generalized formula. Okay, so we're still in general status, right? We still are dealing with a generalized equation. So what do you notice about this side? And what do you notice about this side? On the left-hand side, we have what? We have variables. On the right-hand side, we have constants, okay? On the right-hand side, there's constants. So if the constants are on one side, that means that this is true for both satellites. Does that make sense? So now we could say that v1 squared r1 is equal to v2 squared r2. Does that make sense? They're both equal to the same thing, so they're equal to each other. So this is just sort of a mathy technique that we've used a transitive equality, basically. Everybody okay with that? All right, so now what we're solving for is the green V, right? Sounds like a superhero. Wonder what his powers are. All right, the green V says that V is equal to, what are we going to have here? V1 times the square root of R1 over R2. Does that look right? My math look okay there? We divided each side by R2. Nope, got to divide. I got them upside down, don't I? R2 over R1, R2. Oh, yep. Thank you. R1 over R2. That's silly because these two are proportional. All right. So now we can just plug in the data that we have. So now, since we've solved it generally, we can solve this for the specific equation. So what is important about this right here and the way that we set about solving this problem that was laid out for us? What's important about this right here? That it's true always. It's always true. We did not put anything in that was specific to this problem. We just used general relationships that are true and are established physics relationships. Okay? So, I mean, you can start there if you know what's going on. All right? I would suggest that you get there, and when you get there, you go, oh yeah, okay, this is that thing that we did in class. All right? But it should be a comfort point, if nothing else. It's true for all. All right, so what is V1? Remy, you were reading. No, it was Laura. What'd you get there? What is V1? Loud? 1.7 times 10 to the 4th meters per second. All right, times the square root of, how do their radii relate? Go ahead, we need R1. 5.25 times 10 to the 6 meters. And the other one? 8.60 times 10 to the 6 meters. All right, well, that's nice for us. 10 to the 6 meters cancels out. We just have a ratio of like terms, right? Or of like quantities. So now we get 1.7. Somebody get a calculator out, please. We'll pause for a second. All right, and Brittany says that V2 ends up being 1.33 times 10 to the 4th meters per second. All right, so does this make sense? What did we say about the orbital speed of the outer satellite? It should be less than that of the inner satellite, right? Think about those things that you go to at the store, right? Or when you're at a science museum, some kind of thing. You know what I'm talking about, all those science museums you guys go to, right? You have a little chute over here, you put a penny in it, and it goes around, and it goes, and what happens as it goes down, and it goes in smaller and smaller circles. It goes faster and faster. It's similar to that. This is a conservation of angular momentum idea. All right, but conservation of angular momentum applies to planetary orbits, and is something we'll learn in AP Physics next year. Okay, so that is problem 27. Important steps. What do we do? Remember, it is not true that their centripetal forces are the same. We have to jettison that idea. We know that this relationship is true by canceling the masses and one of the radii. We got to this right here. The important technique we learned, or that we're exhibiting right here, is the idea of putting variables on one side and constants on the other side, so that we can transitively set these two relationships, this relationship for each of the two different situations equal to each other, because they're both equal to a constant up here. Okay? Then it's just a matter of solving, and that's pretty easy. Okay? Then we just spin into oblivion. All right, any questions? Was that number 27? All right, yes. What?